All right, we're going to go ahead and get started. My name is Mike DeLaCluse. I'm the president of Lesman Instrument Company. I'd like to thank all of you for taking time out of your busy schedules to join us for our 11th customer webinar, where we're going to be discussing industrial communication. You hear all the terms thrown around, but I bet you've never heard it broken down in a simple, understandable way like Dan Weise is about to do for you. Dan has been with Lesman for 23 years. Most of his career is our technical support specialist. Dan's the one we go to when we need to get two pieces of equipment to talk to each other. He's not only got to make it work, but he understands it firsthand, how it works, how to get the protocols to play nice with each other. Because of the depth and volume of the material we could present on the topic, this will be a multi-part webinar. I'm going to mute the phone lines.
We call this the Tools, Rules, and Mules of Industrial Communication. And the goal of this webinar is to give you the understanding that any communications link consists of three components. And I use this little graphic up here in the corner, these three pieces of the puzzle, because you need all three pieces of the puzzle in order to make industrial communications work. These three pieces of the puzzle are called Mules, Rules, and Tools, and they correspond to the hardware, the protocol, and the software that are needed in order to make industrial communications work. And without all three, it's not going to happen. And the test of whether we're successful in getting this across to you is whether or not you'll understand the answer to the two upcoming questions. The first question is a consumer communications question, but it's something that anybody could run into at home. There's a new flat screen TV, and it's got a USB connector on the side of it. You plug in a USB mouse, but you don't see the cursor appear on the TV. Why is that? At work, the question could look like this. This is actually a question that was posed on control.com. It's a public forum out there, and the poster said this. I'll read it. I'm trying to send data from a control Logix to a display running Windows CE. I'm trying to do so using Ethernet. Is this possible, or do I have to add something else? You can see at the graphic at the bottom, there's a control Logix processor, and there's a Windows CE HMI panel, and you connect them up, you plug them together with Ethernet, but nothing happens. And this is not an uncommon question in the industrial world. I plug them in, why don't they work? So by going through the rest of this webinar here, I hope to give you the understanding of why the answers to these questions are what they are so that you can understand it, take it forward. As part of this, our agenda is to look at what actually constitutes a communications link, and then look specifically at industrial communications, both analog and digital, to find out why one goes in one direction or the other, and then to look at the tools, rules, and mules of industrial communications, so that when you're done, you'll understand that you need all three components in order to make it work. This is part one of the webinars. Part number two is going to cover the specifics of these mules that carry the data, RS-232, RS-45, Ethernet, and OPC. And then we're going to, part three will cover two industrial protocols in depth, which are HART and Modbus. And again, once you've gone through this, you'll see that you need all three components to make it work. Well, if we look at an overview of what communication is, it's the exchange or transfer of information. And the graphic up here is from the PhDs that work in linguistics. And they've decided that there's data, information, knowledge, and wisdom. We're going to work down here in this first gold circle, where the data is the field data, stuff like process variables, set points, outputs, stuff that happens in the control world. And that data comes in, and when it's displayed so that you can understand it, it becomes information. It might be logged as an historical file, or it might be displayed real time, but the point is it's got to be translated so that it's understandable. In the industrial world, we've got analog and digital communications. I've listed off here the various things that most people want to take a look at, the process variables, outputs, alarms, and so on. This is the kind of stuff we're going to focus on because we live in the process world. Historically, we've had raw analog data out there for years. All of these instruments up there are raw analog, but a human being has to stand in front of them and look at them in order to get a reading off of them. If you add electronics to the devices, then you've got something like 4 to 20 or 0 to 10 or a load cell signal that goes out, can be taken by another instrument, and at least you can do it remotely at this point. But there are problems with analog. You can run down the road of analog, but eventually you run into limitations that just put you where you can't go any further. And then see what they're all listed out there as. We're going to take a look at each one of these individually in the upcoming slides here. The first topic about digital is the comparison between analog and digital resolution. If you look at the upper right up there, you see an analog scale. Obviously, there's a question as to how well you can resolve that. Once you go to digital using A to D converters, you've got 8 bits will give you 1 part in 250, all the way up to 14 bits will give you 1 part in 16,000. But the point being is that when you go digital, you come up with a number that you can deal with rather than having to interpolate it off of an analog scale. Precision relates to how precisely I can read that value, and the problem here is that different people read an analog gauge in a different fashion. One person might read it one way, another person might read it another. Well, if you got digital, you got 9765 down here. That's a set of numbers that everybody agrees is 9765. Now, it might not be accurate, but at least it's 9765. When we take a look at accuracy, that tells us how closely we actually hit the target when we compare that value to a known standard. And the advantage of digital is that because you've got a number, you can actually compare it more accurately to a standard. The other thing is that it can overcome things like voltage fade or noise that you get in an analog signal, because digital numbers don't change when you transfer them from one point to another. They're still digital numbers. An aspect of digital communications which can be terribly beneficial is dynamic range. We see this most often when you deal with totalizers. The reason for that is totalizers very quickly go outside the scale of what is ordinarily represented by a 4 to 20 milliamp signal. With 4 to 20 milliamp, you might have 1 part in 1600, maybe 1 part in 4000, depends on how good both ends of it are. But when you go to digital, an integer is easily plus or minus 32,000, and if you go to floating point, you get numbers that are just are exponential. They can be huge. And this it also comes up with decades of logarithmic information and actually be able to interpret it. A very common circumstance that we run into is dealing with multiple variables. Here we see in the graphic a UDC controller, and the task here is to take information from the controller and record it on the recorder. And we've listed off here what we want to see: the process variable, set point, output, and 3 different alarms. So this is graphically what it's going to look like. I've got to get these 6 pieces of information. I've got to get them into the recorder, and I also got to light up the alarm lights at the same time. So when I go to do this, I make up my little table, and I say, these are my points. Here's how I'm going to get them out. And when I go to wire it, this is essentially what it looks like. I'm going to take my 4 to 20 output, run it to the valve. I'm going to assume that I can series it over to the recorder. I have to add a card to the controller to get an auxiliary output in order to get my set point into the controller. And for the alarms, I have to send them to a relay because I've actually got 2 outputs. One's going to go to the recorder, one is going to go to the light. For the process variable, I'm just going to assume that I've got something like a thermocouple that I can parallel over there. Although obviously if I got an RTD, I got a problem because you can't parallel an RTD over there. I've already used my auxiliary output for my set point. Now compare that to what happens if I use a digital protocol known as Modbus. I still have all 6 items here. I'm going to use my 4 to 20 output to drive the valve, but I don't have to series it over because the output, along with all the other information, can be transferred via Modbus to the recorder. The big advantage here is that the recorder isn't as expensive because I don't have to have any analog inputs or digital inputs on there. And on the controller, I don't have to have an aux out board because I can just take that set point value and transfer it via Modbus into the recorder. So that's an example of how digital communications can cut down on the wiring and get the same information over to the recorder. One aspect of digital communications is consolidating lots of information out into the field, getting multiple pieces of information from multiple devices back to a central point. The way I do that with analog is I got to have a cable with a whole bunch of wires in it, usually twisted pairs, but it's a big bundle of wires. When I go digital, I've got a twisted pair down here, and I can consolidate that information, transfer it from one point to another. The typical application for that is a remote I/O rack that goes back to a host rack. The remote I/O rack has all that I/O coming into it. You send all that data back on a twisted pair to a central point. Once it gets back there, there's always a question of the distribution of the data. How do I get the data to the people that really need it out there? Analog is inherently unidirectional and point-to-point. I can send it from here to the controller and from the controller out to the valve. When I go digital, I can send it from here to a box. It'll take it, and I can send it out to the controller. I can send it to an HMI panel. I can even, in many cases, send it to a browser nowadays, where the browser is going to display that information for me. And if I get bidirectional capability, then I can do things like enter a set point on an HMI, send it to the box. It sends the set point out to the controller. The controller takes care of doing the control. And meanwhile, I'm reading information from the field instrument. And if I have to do a scale change or range change on it, I can do that by sending data back out to the field instrument. Diagnostics have been a huge thing, particularly in the capital-intensive industries out there, where they need to make rapid repairs to a process in order to cut down their downtime. You can read on the chart over here, there's typical bullets of the kinds of information you can get as diagnostics. But again, these diagnostics are only available if you've got some kind of digital system to take them out, because on 4 to 20, all we're getting is typically the process variable. These other things got to come over a digital protocol that gives us that information. Remote data entry is always something that's a challenge in the process world. The old way used to be to rotate a knob up there, and the knob had to be wired into whatever it was going into, so you had to run a wire over there. Nowadays, when we go digital, we've got stuff like keyboards. We've got feedback through HMI displays. This gives us the ability to put the data in accurately and also to distribute the data to multiple points. So whatever I put in here at location A gets updated at location B. HART has been around for at least 20 years now, and HART gives us the ability to set up or configure field instruments out there. And with recent advances in HART, it also gives us the ability to record those settings changes and those configuration changes so that we can track assets. This is, if you compare this to the strictly analog world, you're stuck with pots and bench settings and all that kind of stuff. It's a one-time thing and a lot of handwork in order to record the settings and the setup that's been done on it. Probably the biggest reason that a lot of people look at digital communications is distance. I got to go from A to B, and it's a long distance. How do I do that? And there's all sorts of typical applications for that, some of which are as simple as getting across a street when you've got a plan on, or part of a plan on one side of the street and a part of the plan on the other side of the street. With analog, you can be limited in distance if you're running a voltage. 4 to 20 admittedly goes a mile, but the big issue with long distance is the cost of getting it across a wire or across a fiber optic cable, because typically it involves trenching, or if you got to stick it up on poles, you got all to deal with poles there. Now, telephone is analog, but you can't put DC directly into a phone line like a 4 to 20. You still need a modem and the conversion stuff in order to get the information into a form that will run over a phone line. But once you go there, digital communications can go long distance. The example of the phone line modem can go easily across the city or across the state, across the country. And now what we're into with Ethernet and local area networks is that can go plant to plant, or when you utilize publicly available internet, you can use VPNs to correspond between sites that are literally all over the world. So you're using somebody else's copper or fiber optic to transfer the information back and forth. And it easily handles multiple pieces of information where you don't need a pair of wires for each data source. Now, there are exceptions to this distance thing. Some layers, some hardware is just limited by nature to short distances. Like RS-232 is typically 50 feet. The parallel printer goes 30 feet. And if you go into wireless, USB, or Bluetooth, you're typically limited to tens of feet, 40 feet, 50 feet, 60 feet, something like that, for it to work. One reason we found that people are looking into digital communications is just the replication of a data value elsewhere in the plant, but they want the exact same value. They don't want to send an analog and then have it translated and be off by a little bit. So there are, for instance, panel displays out there that will read a device and give you an exact value somewhere else. Here's an example where you can actually just use two indicators that have the same display on them, or where you have a PLC and you need that value else where you don't want the cost of putting up an HMI panel to give you the same information. But you can duplicate that. And of course, these are considered calibration free because there's no analog involved in this that can fall out of calibration. They're digital numbers that start at one point, end up at the other point, and it's the same number on both ends. So those are a whole bunch of reasons that limit analog. Digital would be nice, and all that's very nice. But what do we have to do to actually get there? Well, there's three pieces of this communication puzzle. There's the mule, the rules, and the tools. And I want to relate these to a telephone call to understand why we need three pieces in there and not just one or two. And the telephone call is an excellent example of this because a telephone call is actually very complex. We don't think of it because we've learned since little kids how to make a telephone call, but it's actually quite a complex series of events. Think of it this way. In order to make a phone call, you got to pick up the phone, wait for the dial tone, dial the number, the other end rings or is busy or shunts you to voicemail. But if it rings and somebody answers, somebody says hello, and you identify each party identifies the other. If you get the wrong party, you then have to determine what you're going to do to get the right party, but eventually get to the point we can have a conversation. This is what we think of as the telephone call, where you talk, I listen, I talk, you listen, and it's the exchange of data back and forth, but you had to go through a whole bunch of stuff to get there. And once you're in the middle of that conversation, you can actually run into the situation where you have to step back for a second because you either had noise or there was an interruption, or in the cellular word, you can actually drop a connection. But eventually, you correct for all that, and you conclude the conversation, and you hang up. In the middle of all that, there are a whole bunch of what-ifs that have to be considered. You know, what happens if you actually dial the incorrect number? What happens if you get a busy signal? And all this kind of stuff here has to be taken into account when you make a telephone call. But because we're humans, and we've been doing this since the age of 8, we don't really think of a telephone call as very complicated. Things generally don't go wrong, but if they do, we know what to do a workaround to make it right. The problem is that in industrial communications, it's not human beings on each end of a telephone call. It's inanimate boxes. So the industrial protocols and the software behind this have to take all of this into account. They have to look at all these what-ifs, and they have to look at all the steps in the sequence in order to make this connection work in order to be successful at this. These images here show you that hidden infrastructure in the telephone system that we don't even think about when we make a telephone call. There's all this stuff in the switching networks. There's all that wire and cable, whether it's up on poles or whether it's buried in the ground, whether it's fiber optic or copper. We don't know. We don't care. We just know that when we dial the phone, it rings at the other end. Or when you go to buy a cell phone, you just, you go to a cell phone store and the guy goes in the back and messes with the SIM card, comes out 3 minutes later, sticks it in the phone, and the phone works. But there's a huge installed infrastructure there that supports what happens when you actually make a phone call. In the industrial communications world, we have to make sure that that infrastructure is there, and that's part of what we're utilizing. We have to make sure that something's there because we're not always doing it over the commercial system that somebody else provides for us. And the components that we're going to use are these mules, tools, and rules. So if we decide that we want to go there, how do we get there? Well, part of this world is the PC on our desk because it's digital, but we're also going to exploit what the marketplace has already given us. You'll recognize these terms up here, HART, Ethernet, Remote I/O, Modbus, RS-45, and so on, because the marketplace has given these as components to expedite or to implement this industrial communications. This is the dreaded OSI model right here that you'll always hear brought up in these forums and seminars about industrial communication. You don't really have to understand the nitty and gritty of this other than the fact that you need to understand that it is layered and there's a hierarchy to it. And I break it down into 3 major groups because they sort of consolidate together because it relates back to this idea that we need tools, rules, and mules in order to make this work. We're going to look at each one of these in turn to see how this works out in the real world. If we look at the part called mules, mules are pack animals, and they carry stuff from point A to point B. But you got to stop and think that there's no mule that's ever packed its own load. Somebody else actually has to stuff all the stuff in the bags and lash it to the mule so that the mule can carry it. And mules don't care what they carry. They don't know. They get a load on their back and they carry it from point A to point B, but they don't know what it is. They don't care about it. They can be very stubborn if they're not treated right. They all have speed limits. They only walk or trot at a certain pace. If they run, they don't run for very long. And they only go where the driver leads them. You can't take a mule and say, Mr. Mule, why don't you carry this load down to town, and when you get something, come back? Because they won't do that. They'll drift off and they'll browse on grass. So they need to be led where they're going. How does this relate to industrial communications? Well, the mule is this physical layer in this OSI model, and the physical layer carries the data. That's the important part. It carries the data. It does so through a medium. That medium can be copper wire, fiber optic, or radio waves. When you go to hook all this up, you got some connectors, but essentially it's going to carry electrical signals at some point. They're back and forth in order to make this all work. And those electrical signals are going to implement various technologies. They're going to have various terms, but essentially they're going to be standards that define what happens with the, what voltages you're going to have and what rates they're going to transmit data back and forth at. In the telephone system, a lot of this stuff here is the mule. It's all the we don't even see and we're not even aware of. Now, I want to go through these point by point because most often what we see in spec sheets is stuff about the mules that carry the data, and it ignores in the spec sheet the more important stuff, which is how do I accomplish the task that I want to accomplish? And mules only carry the data. That's all they do. There's no interpretation of the data, and they don't even care about how the data is formatted that they're carrying. To the mule, it's just ones and zeros that they're transferring back and forth, and they don't know or care what it is. They don't know whether it's a process variable or set point. They just get it from point A to point B. And they can't pack their own load, which means they can't format the data. There's got to be a protocol or a driver there that actually formats the data to get it back and forth so that it's understandable at both ends. And they can be very stubborn if they're not treated right. If you put the voltages from one circuit into another and it doesn't match, you're likely to blow it up, and then you don't have communications at all. If there are speed limits to the communications, it's likely to be down here at the physical hardware layer end because the mules have speed limits. You can read off there the RS-232 can run up to 115K, but you can get 1.5 megabit out of RS-45 and Profibus. It's very important to understand, too, that mules only go where they're led. The mule doesn't know what data it's carrying. It doesn't know actually where it's going to go. There's other things in the system, these protocols and these rules, that have to direct the data where it's going to go and how it's going to get there. This slide lists off what I call the mules of industrial communication, and you probably recognize all of them because you've heard them at one time or another: RS-232, RS-45, Ethernet, Bluetooth, and so on. It's important to understand that none of these things up here define how the data is packed, the kind of data that's carried, or how it's displayed or interpreted at either end of the communications link. I've clipped off in this slide some screenshots of specifications from spec sheets for various products that we have. And in my mind, these are essentially meaningless statements because it doesn't tell you the tasks that you can accomplish with this piece of equipment. It just tells you you've got a mule that carries data there. For instance, this one up here where it says data out, it says data out over RJ45 gigabit Ethernet. It doesn't tell you what you need to accomplish that at the other end. It just tells you literally you got a connector that you can plug Ethernet wire into. Down here we see this one that says, this is a little more informative because it says we have an ASCII protocol that runs over 232 or 45. We can run Modbus RTU over 485, or we can actually run Modbus RTU over Ethernet. That's a little more informative, but you have to understand that just knowing that you can run Modbus RTU over Ethernet doesn't tell you whether you can actually do control or whether you can get data or whether you can configure the device. It doesn't define any of that because that's at some other level in this OSI protocol called the tools that we're going to use. So here's our OSI protocol again. The section that we just went over is this red section down here, the physical layer, the electrical standards that transfer data back and forth and just carry the data. So I want to reiterate again, it might seem redundant, but all these things listed here are essentially just voltage standards. They don't define the data that goes over or the tasks that you can accomplish with them. All that's spelled out somewhere else. So now we get to the part about the protocol, which is a set of rules. And you can tell that rules are things that you can do or you can't do. It's just a set of rules. And this slide here shows it's a fairly good definition because it reiterates it's procedures that control how the communication network operates, the standards under which it operates, and the things like somehow or another I have to represent the data, I have to signal the other end, I have to authenticate that it's actually the right end, and I have to detect errors. The protocol takes care of this kind of stuff here. If you're familiar with the modems from the era when we used to connect to the internet with modems, there were these things called AT commands that one sometimes had to put into a modem in order to make it work right. That's actually a protocol. AT commands are part of a protocol. Data packaging refers to things like the least significant bit or the least significant byte. Does that go first or does it go last? And that's very important because bytes are nothing but ones and zeros, and you got to get them in the right order in order to interpret them correctly at either end. You have to define who talks when and who listens when, because you don't want two devices talking at the same time because they'll override each other and not understand each other. So you have hands shaking and holding forward. All of this kind of stuff is defined in the protocol. Error checking to make sure that the information comes through properly from one end to the other. These are examples of communications protocols that we run into in the industrial world. Everybody's probably heard of HART. That's used widely for configuration of data. It can be used to transfer data, but there's a fairly small niche for that. You'll see that there's all sorts of flavors of Modbus up there, none of which, by the way, are really compatible with one another. And you'll see down here that on another slide that we have protocol converters that can actually convert from one protocol to another. Profibus, OPC, Foundation Field Bus. There's some obsolete ones up here that we still run into, and you should be aware that there's a guy, Husabus, that has compiled a list of 500 protocols out there that have been used in the industrial world, and it's available at that web link there if you're ever curious about how many have ever been done and what their names are and what they're actually used for. Now, some protocols do not specify a specific hardware interface that it has to work with. For instance, Modbus and JBus, they can run on 232 or 485. They're frequently run on phone modems, but technically you could use it over tin can telephones or smoke signals if you wanted to. Other protocols are very specific about the hardware that they work with. HART has to work over 4-20. Foundation Field Bus has to work over H1 or HSE. Profibus PA has its specifications and DP has its specifications. So it's going to depend upon the protocol as to whether or not they're very specific about the hardware layer that they work with. Some of the other things that the rules that we have to deal with are what do I want to say here? You don't actually, as a user, have to know all the rules of the protocol, but you do have to understand that you need a common protocol on both ends. In other words, if you're going to use Modbus RTU, you need Modbus RTU on both ends in order to make this work. You can't mix Modbus RTU with Modbus ASCII. Now, if you've got different protocols, there are devices called protocol converters that will convert from one to the other so you can make the communications link work. But the idea that I'm trying to get across is you need a common protocol. This is a case study of what happens when you don't have a common protocol. We had somebody that had a number of TrendView recorders that were all connected with Ethernet on an Ethernet local area network, and they all talked to a software package, and the software package was able to get data from all these number of recorders. The plant bought a paper recorder, and the specification for that paper recorder is right here on the screenshot. It talks Modbus RTU over Ethernet. So when they got the paper recorder, they plugged in the Ethernet cable, went back to the software, and tried to communicate with the paper recorder, and they couldn't. And the problem here is that the software listed down here in this bullet down here, it talks 3 different protocols, TrendBus, FTP, and HTML. But it does not talk Modbus RTU over Ethernet. So what we had here was a mismatch of protocols, where the protocols can't talk to each other because they're not common. So this is an example of why you need the same protocol on both ends in order to make the communications link work properly. So now we've gone over this part right here in blue. This is the protocol. These are the rules that we need in order to set up the communications link and have it operate properly. So we've gone over Mules and rules so far. The Mules are the RS-232, Ethernet, that kind of stuff, and the rules are things like Modbus, Profibus, HART, and OPC. The tool part is this part here where the tools are the software that is used to make sense of the data. And the example here is I need some kind of software that's going to go out there, fetch some data, and then either make a history of it for me or display it or feed it to my controller so the controller can take care of it. Or I've got a recipe and I've got to feed the recipe at the right time to the controller so that the controller can execute it. That's what the software does. It's up at that upper level where we interface with it. We have GUIs that interface with it, make sense of it, displays it for us. Down here on this model that I talked about before, the software tools really operate in this section over here for information. We've assumed that we've somehow, through the mule and the rules, gotten the data to this point right here. Now I've got to make sense of it, convert it into information that I can deal with. In our world, what the tools are is HMI software like Wonderware, Involution, Scitech, Trend Server, and there's probably 50 other varieties out there in the marketplace that do this sort of thing. We can see that there's a screen up here, typical HMI screen, where it's showing us a bunch of controllers. The screen on the bottom is from a recorder where we see the trends. We also see some digital data on the bottom and some notations on there that tell us what the batch information is. So the software makes the data from the field usable. We can trend it. We can put it up as real-time graphic displays. We can do alarming. We can allow operators to change the set points out in the field. The software, the tools handle that portion of it. I want to take an actual example here. We've got a TrendView recorder. The TrendView actually runs, 5 different protocols here. The TrendView is a web server that who can feed data out to a browser like Internet Explorer, and that uses the HTTP protocol. When the recorder has to transfer blocks of information to the software, it uses the file transfer protocol, the FTP protocol. When you need to change a configuration using the software, there's some proprietary protocol that does that. I don't even know what the name is. It just works. There's a mode where the data can be streamed real time from the recorder to the PC, and that uses the Modbus protocol. And it will also run the OPC protocol, which enables the recorder or the software to transfer data to an OPC client like Wonderware or Scitech or Involution or RSView or Factory Talk or any one of those HMI programs that's an OPC client that also needs the data that's on the recorder or on the software package that the recorder runs. The software tools can be relatively complex like Wonderware, or it can be as simple as a web browser like Internet Explorer. Both of the screenshots here come from instruments that have web servers built into them so that when you connect them to a local area network, you can actually see data from the instrument displayed directly. The top one comes from a pH analyzer, and the bottom one comes from the recorder. And the example here that I use is that the bottom one is actually a bunch of tank levels, and it's used by Doris, who sits in the front office, and her job is to check the tank levels a couple times a day, make sure that when they get down to a certain level that she reorders more stuff that up Internet Explorer, go into this page, take a look at it. She doesn't have to rely upon somebody else to run around and get data values or level values for her, or have to walk out herself. She can actually sit at her desk and get data right on her desktop to show her that using Internet Explorer. So now we've taken a look at all 3 of these things. We've taken a look at the software tools that interpret the data. We've taken a look at the protocols that manage the data connection. We've taken a look at the mules that actually transfer and carry the data back and forth from point A to point B. So in summary, these are the 3 pieces to the puzzle that we need: the tools, the rules, and the mules that make this connection work. Ideally, if you start out, and say, I want to, get data from one point to another, you start at the top and you pick a software tool that is going to give you the data in the best format that you can work with it. However, in the real world, a lot of times we end up with people that say, hey, I've got this device over here and I need to look at it. What software, what do we got to do in order to make that work? And you got to pick a protocol and a software tool that will actually display the data or give it to them in a form that's actually usable. Now, just so you're aware, Lesman Instruments is big into the measuring field. We do a lot with field instruments and some controls, but we're actually not systems integrators, but we do partner with people that can put all this stuff together in order to make it work as a final package. So now I want to come back to the original questions that we looked at. The first one was this consumer communications question, where it came up that there's flat screen TV, and on the side of the TV there's a USB port, and the question is, if I plug a USB mouse into that, can I see the cursor on the screen? Well, if you go to the manual for this, the manual part is over here where it tells us that if you insert a formatted USB drive into the USB port, you can actually view pictures on the TV. So whatever the application is, it's designed to read JPEGs or bitmaps and display them in a slideshow on the TV. It has no driver for the USB mouse. So if we come up to this knowing that we need 3 pieces of the puzzle in order to make the mouse work on the TV, we can see that, yes, we have a hardware mule that will carry the data. It's the USB. Do we have a protocol or a driver for the mouse? No. Do we have any software that makes the mouse cursor usable in any fashion or interprets a right click as a right click or a left click as a left click? No, we don't, because whatever is implemented in the TV is there to view pictures from a flash drive, not to operate a USB mouse. So the TV doesn't have a driver. Plugging in a USB mouse won't make the mouse work. Look at the industrial situation, where we've got the ControlLogix PLC, we've got the HMI over here that runs Windows CE, we plug them in with an Ethernet cable. Let's ask ourselves the same question. Do we have the 3 pieces of the puzzle in order to make an industrial protocol or an industrial communications link work? Well, again, we've got hardware mule, the data carrying capability, over Ethernet. Do we have a protocol? Well, from the information we're given, we just don't know. What protocol does ControlLogix talk? Don't know. What does the Windows CE display talk? Don't know. Do we have drivers? We just plain don't know. Do we have any software that makes this data usable? Well, yes, any HMI display out there has a development tool with it, a toolbox, development software that can be made, that can be used to develop a screen to make the data usable. And ControlLogix, likewise, has its development software. But you have to use these software tools in order to make this information usable on the other end. So we really only have 1 piece out of 3 necessary in order to make this work. So in summary, just plugging in an Ethernet cable, yeah, you get an Ethernet connection, but it doesn't do anything for you because you haven't implemented the protocols to transfer the data back and forth and then interpret it so it makes anything useful for us in the real world. So we don't want any of you guys out there to get left in the analog world when you could be moving to the digital world. And we hope that we've covered these 3 pieces in summary so that you have some idea that you need all 3 pieces of the puzzle in order to do the communications link. And I'd invite you, if you got any questions, to pose them now.
Dan, thank you very much for your presentation. If you do think of some questions in the future, feel free to give Dan a call. He's in the office 40 to 50% of the time. He can be reached at 800-953-7626. Our next webinar is going to cover non-contact temperature scanning. So if you have a web or sheet process that could benefit from having accurate temperature measurement of material, you won't want to miss this session. It will be presented by Amatec Land's technical specialist Richard Gagg, and he'll be the week, and this will be the week of April 28th. Again, toward the end of May, we'll have Dan back to present the next session on industrial communication. So if today's session had some value to you, you won't want to miss the session in May. Announcements will be forthcoming.